Hi everybody. Today I'm going to be talking about autonomous interplanetary orbit determination. So a little bit of background. Current interplanetary orbit determination is done using delta differential one-way ranging. This requires access to the deep space network, which is very expensive and limited because it has to track other spacecraft as well. Delta differential one-way ranging works using two radio telescopes spaced apart by a great distance, and then measures the difference in time that it takes for a signal from a spacecraft to reach the two telescopes. From that, the angle towards the spacecraft can be determined, as well as the range and range rate. However, like I said, this requires access to the 𝑗+sin, which is limited and expensive. As a solution, the proposed idea would make use of highly accurate star trackers and sun sensors and spectrometers in order to do autonomous orbit determination. The basic premise of this is that the star trackers determine the orientation of the spacecraft in the heliocentric reference frame. The sun sensor then determines the angular location of the sun, and then the spectrometer measures the range rate of the spacecraft moving towards or away from the sun. From all of these things, position and velocity, and therefore the orbit, can be determined. So for position determination in the heliocentric inertial frame, we assume that the spacecraft knows its orientation extremely well using state-of-the-art and commercially available star trackers. Once it has its orientation known, it can make azimuth and elevation observations of the sun with the sun sensor. It then also makes azimuth and elevation angle observations of the Earth or another planet using the star tracker. With these azimuth and elevation angles, we can find the unit vectors from the spacecraft towards the sun and from the spacecraft towards the Earth. That the unit vector can be determined by the cosine of the azimuth times the sine of the elevation in the i hat direction, plus the cosine of the azimuth times the sine of the elevation in the j hat, plus the sine of the azimuth in the k hat. The position vector of the Earth is known in the heliocentric frame from a catalog, because we have a timestamp of when we measured the position vector of the Earth, and so from that timestamp we can go into the catalog and determine the position vector from the sun to the Earth. This is both magnitude and direction. Now that we have the position vector from the sun to the Earth, and we have the angle from the spacecraft to the sun and the angle from the spacecraft to the Earth, we can then find the angle from between the Earth and the spacecraft. So now we know all angles in the triangle, and we also know the magnitude of the vector from the sun to the Earth. With that, we can find the magnitude of the vector from the sun to the spacecraft, and that is given by the magnitude of the vector from the sun to Earth multiplied by the sine of the angle between Earth and spacecraft divided by the sine between the sun and Earth. Now the position vector in its totality, both magnitude and direction, is just given by the magnitude of the vector from sun to spacecraft multiplied by the negative of the unit vector from the spacecraft to the sun. So now, in order to determine range rate, we use a spectrometer. Spectrometer measures the wavelength of incoming light and whether the spacecraft is moving towards or away from the sun will shift the wavelength of the incoming light because of the Doppler effect. This shift in wavelength can be directly correlated to a shift in frequency of the incoming light. Once we have the shift in frequency, it is very easy to determine the velocity 𝑟ℎ, the range rate, which is given by the speed of light times the change in frequency divided by the original expected frequency from the light coming from the sun. Once we have the range rate, this velocity vector of the spacecraft can be given as the position vector, the unit vector of the spacecraft from sun to spacecraft, times the range rate divided by the entire vector from the sun to the spacecraft. So now we have velocity and position of the spacecraft in the heliocentric frame, and we can do whatever we please with this. Thank you. And that'll be it. Thank you.